Our world is vertical. Towers of glass and steel pierce the clouds. Millions live and work hundreds of meters in the air. This vertical reality seems inevitable. It seems permanent. But it all depends on a secret. A hidden engine tucked away inside the walls. A simple metal box. We step inside without a thought. We press a button. We trust it with our lives. This is the story of the elevator. It is not a story about a simple lift. It is the story of how humanity conquered the sky. It is the blueprint for the modern city. The story begins not with height, but with fear. Before the mid-19th century, buildings were prisoners of the stair. 5, perhaps 6 stories, was the absolute limit. The highest floors were the cheapest. They were reserved for servants and the poor. To go higher required a machine. But early hoists were terrifying. Powered by steam or water, they were crude and unreliable. Ropes snapped. Platforms plunged. Vertical travel was a dance with death. The public wanted nothing to do with it. Then came a man named Elisha Graves Otis. He was not a famed inventor. He was a 42-year-old mechanic from Vermont. He was working in a bedstead factory in New York. The factory needed to move heavy equipment between floors. Otis was tasked with building a hoist. But he was obsessed with one problem. What happens if the rope breaks? His solution was not complex. It was brutally simple. It was mechanical genius. He attached a large, leaf-like spring to the top of the hoist platform. Above it, he ran the lifting rope. If the rope held its tension, the spring stayed flat. But if the rope snapped, the tension was released. The spring would immediately snap open. Its ends would shoot outwards. They would engage with ratchet bars running up the sides of the shaft. The platform would be locked in place. It was a trap for a falling machine. In 1854, Otis staged a demonstration. He traveled to the Crystal Palace exhibition in New York. He stood on his hoisting platform. It was raised high above a watching crowd. He signaled to an assistant. An axe swung. The single supporting rope was severed. The crowd gasped. The platform dropped. And then it stopped. It fell only a few inches before the safety brake engaged. Otis doffed his hat. "All safe, gentlemen," he declared. All safe. It was one of the great moments in the history of engineering. Otis had not just invented a device. He had engineered trust. 3 years later, the first commercial passenger elevator was installed. It was in a 5-story department store in Manhattan. It was powered by steam. It climbed at a sluggish 40 feet per minute. But it was safe. The psychological barrier was broken. The journey upward had begun. Otis had solved the problem of fear. But the next challenge was height itself. Steam engines were bulky and inefficient. Hydraulic systems, which used a giant piston plunged into the ground, were limited by the depth you could dig. A building could only be as tall as its elevator piston was long. The age of the skyscraper demanded a new kind of power. That power was electricity. In 1880, Werner von Siemens built the first electric elevator in Germany. The technology was a revelation. Electric motors were compact. They were powerful. And they could be placed on the roof of the building, not just in the basement. But a new problem emerged. How the motor connected to the car. Early electric elevators used a winding drum system. The elevator's rope literally wound around a huge rotating drum, like thread on a spool. To go higher, you needed more rope. This meant you needed a bigger drum. The system was impractical for a truly tall building. The drum would become absurdly massive. The solution was a fundamental shift in thinking. It was called the traction elevator. The winding drum was eliminated completely. Instead, the ropes passed over a large grooved wheel at the top of the shaft. This wheel is called a sheave. The elevator car hangs on one side of the ropes. On the other side hangs a massive counterweight. The car and the counterweight are in a constant state of balance. The counterweight typically weighs the same as the elevator car plus 40 to 50% of its maximum passenger load. This is incredibly efficient. The electric motor no longer has to lift the entire weight of the car. It only has to lift the difference in load between the car and the counterweight. It nudges the system out of balance. Gravity does the rest. This single innovation unlocked the skyscraper. Now, the height of a building was limited only by structural engineering, not by the elevator. An intense corporate war erupted. The Otis Elevator Company was the giant. But powerful rivals emerged. Schindler was founded in Switzerland. Kohn began in Finland. ThyssenKrupp rose in Germany. These companies competed fiercely for the most prestigious contracts. They battled on price, on speed, and on innovation. The skyscraper and the elevator became symbiotic. One could not exist without the other. The architects designed taller towers. The elevator engineers found ways to serve them. The Empire State Building was a monument to this relationship. It required a staggering 73 elevators when it opened in 1931. Some were local cars. Others were high-speed expresses to sky lobbies. They formed a complex vertical transportation network. For decades, this network was run by people. The elevator operator was a highly skilled professional. They used a large lever to manually control the car's motion. They expertly feathered the controls to level the car with the floor. They were the human interface for a powerful machine. But the next great leap in technology would make them obsolete. The next great leap would give the elevator a brain. Automating the elevator was an immense challenge. It required replacing the operator's intuition with cold, hard logic. The first automatic systems were vast, intricate webs of electromechanical relays. These were physical switches that clicked open and shut. They formed complex logic circuits. The elevator could now remember which buttons were pressed. It could decide which direction to travel. It could determine the most logical order to pick up passengers. When multiple elevators were installed in a single bank, an even more complex group controller was needed. This master brain coordinated the movement of every car. It worked to minimize wait times. It was the birth of machine intelligence in buildings. We see the legacy of this relay logic every day. The illuminated up and down arrows. The lit button that confirms your call. These were all born in the age of automation. But the clicking relays were just the beginning. The true revolution arrived with the microprocessor. The physical switches were replaced by silicon. The elevator's brain became a computer. This opened a new dimension of control and efficiency. It led to one of the most significant, yet subtle, innovations in modern buildings. It is called destination dispatch. With a traditional elevator, you press a button. A car arrives. You get in. Then you select your floor. This system creates inefficiency. A car might stop at floor 5, then 7, then 8, then 10, each time for only one person. With destination dispatch, the logic is inverted. You select your destination floor in the lobby, before you enter the car. The central computer knows where you want to go. It instantly calculates the most efficient route. It then assigns you to a specific elevator. It might assign you to elevator C. That elevator is now optimized to group passengers going to similar floors. It might only stop at floors 40, 42, and 45. Your journey is faster. There are fewer stops. The entire building flows more efficiently. This software-driven approach is paired with incredible hardware. The smoothness of a modern elevator is no accident. It is the work of a device called a variable voltage variable frequency drive, or VVVF. This drive gives the control system precise mastery over the powerful AC motor. It minutely adjusts the power, allowing for flawless acceleration and deceleration. The jerk of old elevators is engineered away. And at the heart of it all, there is still safety. Elisha Otis's core principle has been magnified 1,000 times. A modern elevator is one of the safest forms of transport ever invented. The car is not held by one rope, but by a group of 6, 8, or even 10 steel cables. Any single cable is strong enough to hold the entire car. There is an overspeed governor, a separate device that monitors the elevator's speed. If it moves too fast, it trips a mechanism that deploys massive, wedge-like brakes, clamping the car to its guide rails. The primary brakes are themselves fail-safe. They are powerful electromagnetic clamps. But they require electricity to open. If power is lost for any reason, the brakes instantly and automatically slam shut. The elevator's default state is to be stopped. Today, the boundaries are being pushed once more. For super tall towers, steel ropes are becoming too heavy. At extreme heights, the ropes can make up half the weight of the entire moving system. Finnish company Cone has developed Ultra Rope. It's a cable made of lightweight carbon fiber. It is immensely strong but weighs a fraction of steel. It enables elevators to travel up to a full kilometer in a single run. The very concept of the rope is also being challenged. ThyssenKrupp's multi-system is a ropeless elevator. It uses magnetic levitation, the same technology as high-speed trains. Cars, called cabins, move in a shaft on magnetic tracks. Because they are not tied to a rope, they can do something revolutionary. They can move sideways. A cabin can go up one shaft, move horizontally into another, and then travel down. It creates a looping metro system inside a skyscraper. It promises to fundamentally change how we design and move through buildings. We began in a world limited to 5 stories. A world defined by the tyranny of the stair. We now live in vertical cities. We ascend 100 floors in under a minute. We do it inside a quiet metal box, orchestrated by an invisible brain. The elevator is the circulatory system of the modern metropolis. It is the engine that allows our skylines to exist. It is the quiet, unassuming, and utterly essential secret that lifts our world.